I'd like to introduce Jeff Williams, CEO of Aspect Security, and he is also the volunteer chair. I wanted to point out volunteer chair of OWASP, the Open Web Application Security Project, and he's going to be speaking on enterprise Java rootkits.
Thanks. Hello, everyone. So today I'm going to talk a little bit about what a malicious Java developer could do. And I want to be real clear here. I'm not talking about malware. I'm not talking about executables or trojaning a binary. I'm talking about what a software developer could do in an enterprise in a sort of a typical development role. So Aspect Security, my company, we do a lot of code review. And every once in a while, somebody comes to us and says, hey, we would like you to look for malicious code in this application. And we usually try to find out why. And usually it's because something happened that caused them not to trust whoever was building that code. So in one case, we were working for a systems integrator, and they found out that one of their subs had a sub who was really, it ended up being two Russian guys who were working out of their garage living in Seattle. That kind of thing, they got really worried about it because it was a government contract. Another one, there were some foreign national developers that had got put on a software project and for a government agency, and they got worried about it. Sometimes it's just because the application is so critical, so a financial application that processes trillions of dollars. And they asked us to come in and look at the code from a malicious point of view. So I was watching Office Space, and I was thinking about this attack these guys tried in this movie, and I was like, would that really work? How reasonable is it? I mean, we look at code for this stuff, but is it really plausible that someone could put malicious code in an application and have it execute and generate them millions of dollars or cause the enterprise to fail? Or what could they really do? And would they be detected? So I sort of treated that as a challenge. I said, okay, let's try a little experiment. Let's see what a relatively normal developer, me, could do in a week on that problem. And I'll say, I'll restrict myself to just what a normal developer could do. You can write code, you can turn it over to a CM server. I'm assuming that the build server is out of their control. And I'm assuming the only machine that they have control of is their development machine. So those are sort of the restrictions. I said, I'll keep it to just pure Java. So let's look at, so here's what we're going to look at. So I'm going to talk about what is an enterprise Java rootkit. We'll talk about some techniques that developers might use in order to hide their attacks. So one thing they might do is they might try to turn data into code. We'll look at that as a technique for hiding attacks. We'll talk about hiding these, their malicious code from source code analysis, both manual and automated types of code analysis. Then we'll talk about some things that you could do if developers Trojan libraries, either in their environment or in the runtime. Then we'll talk about the build process. And there's some interesting things that an attacker can do by targeting the build process, where the applications get tested and turned into an executable. And then at the end, we'll finish up. We'll talk about some ways of keeping this malicious Java out of enterprise applications. I want to invite you to an OWASP meetup that's happening right after this talk. It's in the Genoa room, which is on the, I guess it's the third floor, I think. But we're going to have an OWASP meetup there and continue the discussion there, and we have beer. So please join us. There's a lot of code in this presentation, and a lot of materials. So if you're interested, there's an extensive paper if you like to read stuff, and there's a Eclipse project that you can download and load up in Eclipse and open it up and run all the demonstrations yourself. So if you're sitting too far in the back and can't read some of the code on the screen, by the way, you're welcome to move up now if you like, because there are some slides with code on them. Please download it and check out the examples yourself. It's all free and open. All right, so let's talk, what is a Java Enterprise Rootkit? This is an example of a little piece of code that will allow an attacker to download any file off of a server. It's very simple. It just takes a parameter, which is essentially a file name, and then it streams out the content of that file in the response to the HTTP request. So a malicious developer might stick these few lines of code in an application in order to steal stuff, if they want to make stuff accessible off the server. But it's a little bit obvious, right? A good code reviewer would see this and say, hey, what the hell are you doing? You can't allow someone to steal any file off the server. We do find this flaw, by the way, pretty frequently in applications, just developers making mistakes. But it's fairly obvious if you're a malicious attacker. So when I talk about a rootkit, I'm talking about a technique that a malicious developer would use in order to try to obfuscate this attack, to make it difficult to uncover. So one thing we got to get out of the way is, a lot of people have this assumption that Java is secure by default, and that some of the kinds of things we're going to talk about in this presentation are not possible. So I got to start with a little disclaimer. First of all, I want to be really clear that I think Java is an excellent environment for building secure enterprise applications. None of the other environments are any better at any of this stuff. I just happen to know a lot about Java, so I'm focusing on that. But we still need to focus on these kinds of attacks. I think they're a serious risk. So let's look at that. In terms of likelihood, when you think about a risk, you got to think about the likelihood and impact of an attack. So in terms of likelihood, there's essentially no protection, and many of these attacks are going to be virtually undetectable. So in terms of likelihood, all we're left with is the number of developers that touch your application stack. So let's think about that just real quick. You might have 100 developers on, that have access to your project, but that's not all of the developers that are in your stack, right? You're probably using a bunch of libraries. Well, all those developers are part of your application stack. They're all running code in production that's fully privileged. So that could be, I think, fairly likely that one of those developers might get themselves in trouble, might be convinced to insert a few lines of malicious code. Maybe not even by themselves. Maybe somebody approaches them and say, hey, I'll give you some money to insert some malicious code in an enterprise application. I don't know how much that would cost. I think it'd be kind of interesting social experiment to try to find out, but I don't think it would be very much. And then in terms of impact, what could a malicious developer's code actually do? And there, really, the sky is the limit. So we're going to see that these attacks could do virtually anything on that host that a developer would want to. So ultimately, I think that not considering this risk is reckless. One thing I wanted to address is that there are a lot of real code examples of these kind of techniques in the report. And the reason that they're there is because I think it's very difficult to talk about these kinds of security issues in the abstract. If we don't have concrete examples, I think most people will blow off the discussion. So I think we need more research here, and the reason to make it concrete is so that we can really understand what we're talking about. It's important to remember that developers have full privilege in production. I see a number of organizations where they don't allow developers to touch production machines, and they think they're getting protection from that. But they're really not, because the developer can already run code in production, right? All they have to do is turn it over into CM and wait, and their code is going to run in production. So that control, the procedural control of not letting developers touch production, I don't think is buying us nearly as much security as we think. And we got to talk about the Java sandbox. So in 1996, when Java 1.0 came out, I was hired on a contract by the NSA to work with Sun to build this new security sandbox. And we were consulting with them because the NSA was very interested in this technique. And so I got really into the sandbox, and I thought it was an interesting security control that could really work to minimize the risk associated with running code that you don't fully trust. Well, unfortunately, now we're 13 years later, and none of the major Java web containers run with the security manager on by default. So that means that code that runs on those servers is running with full privilege. It can do pretty much anything it wants. And what's even more disturbing is that although they all support running with a security manager, they really discourage it. If you go to the documentation to read on how to turn the security manager on, they pretty much make it seem like it's a bad idea. They're not encouraging it. There's no tutorials on how to set it up and figure out what privileges your application needs and all that. They really encourage you to run with the security manager turned off. All right, so the first technique we're going to look at here, or set of techniques we're going to look at, is turning data into code. And if an attacker can do this, that means they can hide the attack in data somewhere, in a string that's hidden somewhere, maybe it's in the database, maybe they read it in from an HTTP request, and then they convert that data into code that runs. That means that in the application that gets deployed, the attack's not even there. The attack's going to get loaded from the outside and converted into code and then run. So this is a really useful technique if you're trying to hide some code. Here are a few of the places where you might think about hiding a string in Java code. It's really pretty simple to find places where you might put an attack. You could hide it in a byte array. You could assemble it from other strings. You can encode it some way, like with a base64 encoder. You might read it from the request. In this case, we've got a request, a get header that we read that's got the data in it. Or you could get it from the database. Or you could override a toString method and generate a string programmatically. It's a lot of different places. This is just scratching the surface. So how do we take that data and then convert it into some code? Well, the first technique is that we could just write it out onto the class path as a class file. Then it's available there, and when you try and invoke it, the class loader will find it and convert it for you. So this is pretty easy. Here we've got an example of just reading in the code from we've got it in a string here essentially, and we decode it, and then we write it out onto the class path, and then we do that class.forName call to convert it into a tag. And we've got a little method down here that searches through the class path for a directory that's writable. And if you find a directory on the class path where you can write a class, then you can run it. So this is pretty simple. I'm going to run this. And what this did is it ran, and then it popped up a notepad window here, because the class that I loaded contains a runtime.exec on notepad. Now I'm going to use that runtime.exec as an example of something malicious that the application could do. There's a zillion things the application could do that are really malicious, and I point out a number of them in the paper, but for the purposes of today, we're just going to use this runtime.exec as an example of the machine is essentially owned. Okay, so that's pretty simple. Another thing they might do to convert data into code is they might run the Java compiler API, which is really damn convenient. Now you might be saying, why would people run a compiler on a production server? Well, it turns out you have to in Java, because in order to run JSPs, you need to be able to compile the JSP, and it compiles it to Java, and then it compiles it down to bytecode. So you have to have the compilers there. So it's actually amazingly small amount of code that you need in order to invoke the compiler, generate a class file, and then run it. So here we've got a little class that's just, we're creating dynamically called Notepad Launcher, and we're going to run notepad.exe, and that's all it takes. So we ran it again. Here's Notepad popped up with the source. You can do the same thing with the JSP compiler. You can invoke it programmatically. Or in this case, we're going to write a JSP file out into the web directory, where when someone browses to it, it'll get compiled and executed. So in this case, this is actually some pretty reasonable looking code. It's like you might find in a typical report generator engine. All this thing does is it's supposed to generate an HTML file that contains the report and some data. But if the attacker sends a specially crafted URL here with the file name being attack.jsp, and then inside the title, which the title ends up going inside the content here, it's got a less than and a % sign, which signals the start of Java code inside a JSP. So when this thing runs, it'll save off this file with this malicious report, and then when the attacker browses to it, it'll execute their code. So another way of converting data into code. One kind of elegant technique, I think, is to use the class loader. And here we've got an example of how simple this is. In this case, we've got a string here that we read in. It's just hard-coded, but you could read it in from a parameter or from anywhere. But we take in a string of data, and then we convert it into code by calling the class loader. And here we've got an anonymous inner class that overrides the we define an extra method called x in this case that calls the define class method. Now, normally you're not allowed to call the define class method, but we use this anonymous inner class to expose it. So this converts it into a class file, and then at the end there you see we call new instance. And what that does is it causes that class to be loaded and will run the static initializer on the class. So if we put our attack inside the static initializer, when we run this code, it'll execute. So let's give that a try. Just want to run here. So in this case, the attack ran. It converted those bytes into a class file, and then created a new instance which ran the attack. So I think that's elegant. Just one line of code that someone could slip in very easily. And people do use class loaders in their applications. They use them to bring in plugins and other kinds of code. So it's not impossible that an application would have something like this in it. And then the last example I want to talk about converting data into code was something I tripped over accidentally. And that's actually a lesson here, is that there may be more ways of converting data into code inside Java. I was sort of restricted to a week. So I don't know all the APIs in Java. This one I happened to trip over. It's called the Java Instrumentation API. And let's see, so the way this works is in Java 5, Sun introduced this capability where you could attach an agent to a running VM. And typically what you're supposed to use that for is to instrument the classes for timing and profiling information. You can add debug information to the running application this way. But it's really powerful. It allows you to redefine a class at runtime inside the JVM. Now in Java 5, it would be difficult to attack because you have to invoke Java with a command line parameter that specifies that you're going to use instrumentation. So that would be difficult for a normal developer to use. But in Java 6, they changed that. And this is actually a weird trend that I'm seeing, is that things are getting easier and easier for attackers to do. Java keeps making more and more things programmatically available, which opens them up to a malicious developer. So in Java 6, you can do this all programmatically. And here's how it works. First thing we have to do is define an agent. And in this case, the agent just grabs a bunch of bytes and creates a class definition. And then it calls this call instrumentation.redefine classes. And it just passes in that new class. And that's all it takes. So what do we need to do to attach this agent to the VM? It's not much code. All we have to do here is we have to write out, the first thing we have to do is we have to write a jar file containing our agent onto the file system anywhere. It doesn't have to be in the class path, which I thought was weird. But you can write it out anywhere on the disk. And then this code here, I'll talk about this a little bit later. This creates a Trojan version of this class called innocent. And all I've done is change the toString method so that there's some extra instructions in there to call runtime.exec. So I'm just wedging in some instructions. I'll talk to you about how I do that later. But for now, all we need is these bytes. You could actually just read these bytes in from a malicious file or wherever. Then all you have to do is get the PID, and that took some doing, by the way, to get the process ID of a running JVM. So I figured out a way to do it that's not very well known, but this works. You get the VM, at least on Windows. I'm not 100% sure it'll work on other platforms. And then you call vm.loadAgent, and we're just attaching the agent to our VM, and then it can do whatever it wants. It can change classes at runtime. It can do anything. You can change how Java lang string works if you wanted to spy on an application. You could change how inet address works if you wanted to make it do DNS spoofing, or override how this thing calls DNS. You can do anything you want. And so let me run that. So here what you'll see in the output is that we call innocent first. This one just printed the word innocent. It's the normal toString method that it's not Trojan. Then we wrote out this jar file with our agent in it, and we had to include a couple parameters in the manifest. We had to define can redefine classes and can retransform classes. And I think that's a little bit weird to put those are really security relevant properties. I think it's weird to put them in the manifest of like some random jar file. But that's how they did it. So you put those manifest entries in there, and then you start the agent, and it Trojans the class, and then we called toString on the innocent class again, and our attack ran, and we got this notepad that popped up. So very, very powerful technique. If you wanted to spy on a running VM, you could do just about anything with the instrumentation API. All right, so in the next section, I want to talk about some techniques for, some other techniques for hiding from source code analysis. And when I talk about source code analysis, I'm talking about a human expert armed with some really excellent tools. And that's really the only way to do source code analysis. In the old days, like in the late 80s and early 90s, I was part of teams that we would sit around the table with the green and white striped fanfold paper, reviewing code by going through it. Those days are gone. You can't really do source code analysis that way effectively because applications are just too big. You need tools like editors that have good search functions and allow you to navigate the control flow easily. You need more powerful tools that do data flow and other kinds of analysis as well. So when I talk about source code analysis, I'm talking about a combined approach that uses the best, people who really understand security and some really powerful tools. And then we could talk about some of these techniques that can be used to mess that process up. All right, so you can use psychological operations. Good code reviewers make assumptions about how code is supposed to work. They'll look at what common methods are, and they'll assume the behavior of those methods. They'll use misleading names and misleading comments. They'll assume that methods do what they look like they're intended to do, because you don't have time to go into every nook and cranny of an application typically. That would be extremely expensive. One thing that I think is an easy way to do psychological operations is to take advantage of some of the Java puzzlers. And if you go to this site and get this book, there's some fascinating things about Java. All the corner cases about the way things behave, you can really use those to your advantage to mess up a code reviewer. And even if you're using a tool, a tool's not going to get fooled by many of this PSYOP stuff, right? But even if you're using a tool, you're going to generate a ton of findings. And then guess what? A human has to go check out those findings to see if they amount to anything real or not. And if you can fool the reviewer, who's the analyst, who's looking at the code into thinking that it's a false alarm, then the attack's going to stay there anyway. I like the idea of attaching a suppress warnings annotation to your attack as well, because it makes it look like somebody already analyzed it and said, hey, you know what? There's no problem here. Another technique that I think is really important is to make overpowerful methods. And I'll give you an example, is the best way to explain it. So here's two different methods, both of which create a connection to a database. In the first one, the driver is hard-coded. And when you call a class.forName on it, it's just going to invoke that particular driver. But there might be some developer out there who says, hey, you know what, I want to make that parameterized. I want to have a method that's a little more general. And so they pull the driver out as a string and allow you, maybe they're making it declarative so you can configure the driver. Well, in that case, now you've got a class here that will do a class.forName on whatever class you pass in, whatever name. So the technique here is to take the code that does the attack and split it up and move it into methods that do one little piece of your attack for you. Both of these methods would pass a code review no problem because they're both legitimate. But this would mean that you'd have to now chase down every place where get connection is called and make sure that it's being used for a legitimate purpose. So here's another technique that you might use. This builds on reflection. So most people think that in Java, strings are immutable. Talk about it all the time. But actually, they're not. If you're not running inside a sandbox, then you can change strings. And here's an example of some code that does it. So we've got a private final static string declared up here. And our main program just prints out the original string. Then we call this change string method. And we'll change it to foobar. And then we're going to print out the string again. Here's all it takes to change the value of a string. Now imagine you're reviewing some code somewhere completely different in the application, and you're reading along, and it says there's a private final static string, and you go down and there's some code that relies on the value of that private final static string. Well, you're going to allow that. You're going to allow that code because it looks legitimate, but if you can't trust the value of not just strings, but really any object, you're going to mess up the review. Let me run that. So here you can see this is run on Java 1.6. It works a little bit differently in some other VMs, but here we've got an example. So it runs. You can see there's the original string test, and then down here it's the string foobar after we changed it. Let's look at another example of a way to abuse reflection. This is a way to invoke a method with reflection. We're calling class.forName to get a method, and then we're going to pass in some parameters, and then we're going to invoke it. To obfuscate this a little bit, rather than saying like class.forName runtime and then get method exec, we hide the parameters inside this base64 encoded string. So inside there's a bunch of methods that say basically runtime.exec notepad.exe. So that's a way of invoking methods without actually, without actually running the code, or without actually making it look like you're running the code. I guess this one invokes calc. All right. So here's an interesting way of obfuscating an attack. This is legitimate Java code. See, Java supports the Unicode, and it allows you to encode any character in a Java source file as in this \u format. What I think is weird is that it also allows you to encode normal alphanumeric, normal ASCII characters using this format as well. So you can use it to obfuscate stuff in your source code. So here's what this actually looks like if you decode it. You can see we've got a normal Java class. We've got some comment characters here at the beginning and ends of the lines to make things a little more complicated. But this is just normal code that will run. Here, let me hit this. So this application, you can see, will runtime.exec notepad. And that's a little bad. If you want to look at a really crazy example, I found this searching around the internet. And this is some code in a real application out there. It's massively encoded. And if you download the source for this talk, it's also in that archive as well. But it's massively encoded code using this technique. And then even if you decode that stuff, it's been obfuscated pretty heavily after that using some sort of code obfuscator. So very complicated. I don't know all the things that it does because I didn't bother to figure it all out, but it's a good puzzler. Some other examples of how you can use this technique. Here's an example of putting an end quote and then a semicolon, or I guess end quote, end paren, and then a semicolon, and then a runtime command in the middle of a string. So that almost looks like it's an unterminated string. If you want to terminate it, you can add some more code that has another string. And then here's a weird one. This is using some comments. And I found out just through a little bit of fuzzing that you can use an unlimited number of slashes and an unlimited number of U's. The Java-C parser handles that. So you can make these weird patterns. Inside here, there's some other code, and it all looks commented out, but some of these first characters are the uncomment character. So the code gets commented back in and runs. There are some tools associated with in the download to deobfuscate code and give you some warnings. If a baseline has any of this encoded code in it, you can quickly find out. And let me run this. This one actually there's 4 different runtime.execs in that little example. There's 1, 2, 3, 4. Inside one little chunk of code. So this is something that a code reviewer, if they didn't know that trick, they might easily miss. Fortunately, the static analysis tools that I looked at understand this. And so they will find the problems. But if you're using a homebrew static analysis tool or maybe some open source thing, it might not understand this encoding format, and it might mess it up. OK. Another way to mess up code analysis is by, and fundamentally what we're talking about here is using the architecture to trip up the source code analyzers. If you want to do good source code analysis, you've got to understand the framework that the code is running in. So here's a little example of a filter. If you don't understand how filters work and how they're mapped in web.xml, you might not understand that this code executes before the application and will run in advance. So then when you're looking at, if you just looked at the servlet by itself, you wouldn't understand that this code was there. So in this servlet, this filter, there's a little trick. We create a servlet request wrapper, and we're wrapping every request that comes into the application in a HACK request. And we're defining it in a anonymous inner class here. We're overriding the isUserEnroll method so that if the attacker passes in the backdoor parameter, then we override this isUserEnroll method to return true, always. And if you look at these, the logic here, it'll always return true. Otherwise, if there's no backdoor parameter, we'll just call the isUserEnroll method as normal. Now, a real attacker wouldn't say backdoor, right? They would say if the user agent ends in a whitespace character, or if the some other parameter is capitalized. Right? They'd make some very subtle change to the message so that you wouldn't normally notice. They might even take this code and move it out into some other method, like do security check, and bury that inside some other filter so that no one ever really realizes what's going on here. Another way to abuse filters, and again, I think there's this architecture point here that I'm really trying to make, which is that you can't do this code review without understanding the architecture. Here's a filter that will bypass the authentication and access control rules that are defined in web.xml. And how it does it is by using a forward. So when a request comes into an application, you can set up in web.xml, you can set up security constraints that define what role you have to have and what authentication is needed on that request. But it only happens on the request when it comes in the front door. If later within your application you forward to some other part of the application, there's no access control check done on that second forwarding. So if a malicious attacker sets up a forwarder, they can potentially go around access control rules that were intended to stop non-administrators from accessing administrative functions, things like that. So it's really pretty easy to do this. You set up the query string and then you forward this request on to the target, which is your malicious code. And this is cool. So Servlet 3.0 has just come out pretty recently, and in the Servlet 3.0 spec, now you can define servlets and filters programmatically. So you can add a filter to your application programmatically. That's going to be difficult for an analyst to find and understand. And certainly for automated tools, it's going to be difficult for them to analyze an application and see what filters are actually in place at runtime, because now it's controlled programmatically. Did you get that, Dennis? It's going to be tricky. Let's see, a couple things you can do with data flow tracing here. So one of the things when you're tracing an attack through some code, you want to be able to follow the data to see where it goes, to see if there's a path from some untrusted, tainted data to some sink that will do something bad. Here's an example of calling a validation method, which looks legitimate. It does, does some simple validation here. And probably the tool or the reviewer would say, hey, it's validated data. I don't have to worry about it. We don't have to trace the taint any further. In this case, though, the parameter comes out of the request here, and it's tainted. We validate it. But we've done this base64 decoding on it. Did I get this right? Yeah, we're validating the original parameter. No, that's not right. Anyway, so sorry, I think I messed up my example. But the point here is that you can use a base64 encoded parameter, for instance, to bypass the validation rule and get potentially tainted data into an application. Another way of abusing taint tracing is by storing tainted data and then fetching it out in some other part of the control flow. So it's very difficult to trace through the code if the data disappears into some database and then some other place a query pulls it out. You really have to understand exactly what query is running in order to know what part of the data is tainted. So in this case, we're hiding a dirty parameter here from the request, and it's got a URL in it, and we pull it out, and we store it in a request attribute, and then later on we pull it out of the request attribute, and it becomes part of some JavaScript. Now this is a really trivial example because it's very difficult to put one of these in one slide, but in the real world, these are much more complicated, where data is getting stored all over the place on the back end, and very complex objects are being used, and it's difficult to to keep track of the thread. I'm sure Dennis is going to chime in that O2 can do this no problem. But it takes a human reviewer to piece together all these threads of an application to follow the taint all the way through. Here's another example of how understanding the architecture is critical for doing source code analysis. In this case, we've got a little chunk of code that invokes a new thread. And there's this puppy class, which is a runnable. And when you call start on that runnable, under the hood, Java will invoke the run method. So if you don't know that, then you may not look at the run method when you're tracing through in Eclipse or following through the control flow. If you don't know that the run method is what's actually going to get invoked under there, then you're going to miss that code. It's not going to be part of your analysis. There's lots of places where that kind of thing happens just in Java, but it's really nuts in the frameworks that do inversion of control, where there's like struts and Spring and so on. Those frameworks invoke code all over the place that if you don't understand how the framework works, you're not going to know what code ends up getting run. And let's see, the last example here is a way of sneaking data into an application in a way that would be very difficult for an analyst to see. So in this case, I'm sneaking an attack into the application using a timing channel. It's actually pretty easy to detect the timing between HTTP requests because Java's got this call called getLastAccessTime, or session.getLastAccessTime. Then it just tells you the last time the session was accessed. So if you compare the current request's time to the last time the session was accessed, you can get a good idea of how long it was since the last packet. So now imagine using that kind of like Morse code, right? So you're streaming an attack in bit by bit using the timing between requests as the signal. So just to demonstrate that, I've got a little example of that. There's a million different timing channels that you could think about using here, but I'm going to start a Tomcat server. And then I'm just going to, and it's running a little receiver program that just receives these bytes and bits actually. And as it receives bits, it adds them onto a long string. And then I'm starting this sender program, which is just going to start streaming these bits out. So let me see if I can figure out a way to get this down to the bottom. So here's, we've got two windows. They're streaming essentially in parallel. And it takes, 3 or 4 minutes for these attacks to for all this data to stream in for a malicious class, but it's pretty reliable. And once these bits are all received, then this receiver program says, okay, I've got all the timing, and I'll invoke an instant. It converts it into a class using the class loader, and then it invokes it as an attack. So if you went back to try to trace this attack, you'd never find this in the logs anywhere because all the data is in the spaces between the requests. It would be very, very difficult to detect the attack coming in. I'll just leave that running. Okay, let's talk about Trojaning libraries. Talk about a couple different kinds of libraries. Let's imagine that you wanted to do some real damage, not just to your organization, but maybe to a bunch of different organizations. You might go find an open source library like Log4j or Struts or something that a lot of people use. Imagine what would happen if you could Trojan Log4j. Right? I think probably all of the Fortune 500 companies are using Log4j in production. So what would you have to do to Trojan it? Well, you'd probably have to make some good commits to it, like make some real improvements to it and become a committer on the project. And then put in a backdoor somewhere in one of your commits that probably it does some other good stuff. Now you've got a backdoor in a library that's going to run in production in most of the Fortune 500. You could literally own the entire financial industry in one shot if you were able to do this. And it wouldn't be ridiculously hard. So here's a little example of how you might Trojan Log4j. This is a little obvious. I think you could do a little better than this probably, but I only had a week, so what are you going to do? This one, it allows the attack to be streamed in from the outside using log messages themselves as the channel. So I'm counting on people actually logging parameters from the HTTP request. So if you use this library in any application that logged parameters from the HTTP request, those messages would go into Log4j, and Log4j would call this, and we added a little, in the log warn method, we called this little sanitize method, which is, it's just fake, right? It says it handles, TLA, multi-part byte Unicode byte ordering, which I just made up. And I have some signals, right? So if it sees a message that starts with FFFE or FFFF, then it grabs a chunk of that parameter and starts adding it on to an attack that's being built over time. When it receives the whole attack, then it invokes it. It creates a class out of it and runs the attack. So this it's feasible. Might not work in every organization, but I think it's conceivable that this would work. And I don't know if people would notice this reviewing the code. I don't know of any organizations that are actually reviewing the code for Log4j. Most of them just grab it and include it in their application and run it. So let's take a look at this. This runs pretty much the same as all the other demos. This one runs, it says, it's received these parameters, and then, I made a bad change there. But this attack runs no problem. So remember a little while ago I said I'd tell you about that Trojaning class files. Well, it turns out that you can, if you want to Trojan a class file programmatically, you want to insert some instructions in there, you could make a bad version of the class file and of the Java file and then compile it to get the bytes of it. Or you could do it programmatically. And it turns out it's not that hard to do. I was poking around in rt.jar, and there's a lot of interesting stuff in there. But one of the things that I accidentally saw was that they included the whole Apache bytecode engineering library inside rt.jar in the JDK. Well, that library allows you to manipulate bytecode programmatically. So I wrote a little program that just, it searches through a class, it grabs a method out of it, whatever method you want, and it pulls out the instructions. Here we get this instruction list. And it creates a couple new instructions. It invokes a runtime.get runtime, and then it invokes runtime.exec, and it passes in notepad.exe. And then it puts it all back together, right? It builds a new instruction list and shoves it back in the class. And then you've got this Java class object, and there's a call in Java class where you can just call Java class.getBytes. So you grab the bytes for the new attack. And then you can overwrite the class file that in the running application. You can use that Trojan class file in a lot of places, and we'll look at some different ways you can use that. But this is pretty easy if you want to just, in this case I'm Trojaning the toString method to have a call to runtime.exec, and it just launches up Notepad. So yeah, thanks to Sun for putting that right in rt.jar. It's useful. Now, if you want to Trojan a jar file, you can create a jar file programmatically very easy. And if you want to overwrite something in the production environment, you could just overwrite one of the running jar files and, or put it on the class path somewhere in front of the jar file that's actually running. So this little example, it takes one file and it sticks it inside a jar file and writes it out to wherever you want on the disk. So you could use this to override a class, whatever class you want, if you want to make a malicious class. And you can even generate a sign jar file if you like. It takes a little more code, but you can generate a sign jar file if you want. Now let's imagine what would happen if you used that same technique to Trojan the Java installation. Well, you could do that pretty easily, right? You just overwrite one of the files that's in the JDK. There's a lot of jar files. Oops. Oh, that's the timing attack finally finished and just ran. The bytes all came through. Now here's an example of, we're passing in just one parameter, and we're going to write out the bytes that we got from that parameter out to a jar file. So if you pass in, a serialized jar file, you can just reconstitute it on the class path. This is a pretty simple JSP. So I can imagine someone throwing this onto the, into their web directory and putting, trojaning the Java installation in production. And this would probably stay this way for a long time until somebody reinstalls Java on the server. Oh, and one nice trick is there's an ext directory in the JDK, and any files that you put in there, any jar files that you put in there, are automatically added to the class path for that application, and they get all permission. Even if you're running a security manager, those classes in there get all permission. So if you look in there, I'd be willing to bet in your directory, in your JDK, that you've got qt java.zip stored in there, which is Adobe's little trick. They put a jar file inside the ext directory in your Java. So I thought that was a nice way of getting around any potential security policy problems. All right, so our last topic today is we're going to talk about owning the build process. And we've gone way beyond the old days of makefiles and Java-C. And I wanted to point out a paper by a guy named Ken Thompson called Reflections on Trusting Trust. Probably many of you have read this, but if you haven't, it's very short. It's like 3 pages, but it's a mind changer. In Reflections on Trusting Trust, this guy named Ken Thompson, who is one of the original guys who worked on BSD Unix, he talks about a sort of a thought experiment that he did, and he actually wrote the code for it. But what he did was he decided to put a backdoor for himself in the login program to Unix. And then he decided, well, somebody's going to see it in the source code, so I got to get it out of there. So he decided to Trojan the compiler so that every time it compiled the login program, it would put the backdoor in for him in the executable. And then he thought about it. He said, yeah, but somebody could see that in the compiler source code. So I got to get it out of there. So he said, I know what I'll do. I'll Trojan the compiler again. So when the compiler compiles itself, it will put the backdoor in the executable compiler. And then he'll delete the source code. And then from then on, every time anybody compiles either the login program or the compiler, those backdoors will be built in, but they won't be in any source code anywhere. So no one would ever find them. It's a great paper. It'll kind of blow your mind. And it makes you think about all the things that we're trusting when we run some code in our environments. So I just took a look at sort of a modern build environment. And a pretty common one that's based on open source tools that's used in a lot of enterprise is this chain that involves Maven at the core to do the actual build, and then Hudson as a build server. They call it a continuous integration server. They'll rely on a repository called Nexus, and they might use Subversion. When you look at this set of tools, so I installed them all, and then I started digging around inside them. I found that it's an incredible amount of code in there. At the end of the day, it ends up being like 16 million lines of code across all the jar files and all the stuff that gets compiled in, and about 500 different open source projects required to build that. So imagine how many developers that must be out there. Maybe 500, maybe 500,000, I don't know. There's really no way to know. But you're trusting all of those developers in your production environment, because anyone who can control the build process, as Ken Thompson showed, they control production. It's very easy to Trojan class files and as part of the build process, and then those Trojan files will run in production. It's also really sneaky because nobody looks at this stuff. Right? People are downloading new plugins for this kind of stuff all the time. They're like, hey, I need a dashboard that shows me the code coverage on so-and-so with a hierarchical vector plot. Okay, great, load the plugin. But it all runs on the build server. So I want you to think about your build server and how you can go about protecting it from some of these kinds of malicious code. I took a quick look at Hudson. from a security perspective. Spent a couple hours, and what I found was really disturbing. I found, not looking very hard, a bunch of cross-site scripting holes and a bunch of CSRF problems, which were really bad. One of them was a CSRF to Jython interpreter. And if you inject Java into that parameter that goes into the Jython interpreter, it'll run, and you can inject an operating system executable through that. So you could run a native command on behalf of the admin in the build server. So there's the exploit. There's a few others, but I don't think that people building these build tools are really thinking about security the same way that you and I might. I did report these, by the way. They said they're fixed, but I haven't verified it, so might be out there. I don't know. So let's look at a couple other ways you can abuse a typical build process. So here's Ant file. Ant is another tool that gets pretty widely used building enterprise Java programs. This is an Ant task, and it invokes a Java program. And we're invoking this B-cell program that we just looked at. That's the one that Trojans a class file, right? So what this does is it says, I want to Trojan this user account class so that anytime somebody does a toString on the user account, it's going to run that runtime.exec. Now, someone could slip this into the build.xml file, maybe obfuscate it a little bit, use some parameters and things to make it a little more complicated to figure out. But they could use this to Trojan an application. So it's pretty simple. I'll run it because I like to prove that things work. So here's the dist just ran, and when the build runs, it executes this class, which we could then use to Trojan class files. Remember that if you do that attack, then that's going to run on not only the build server, but also probably on every developer's machine, because they're going to sync to your build.xml, and they're going to run that when they build the application on their desktop. So now you've got control of not just the build server, but also all the developers' stuff. So then I started thinking about, well, what could a developer really turn over that would run on the build server? Like, it's a little tough to, build.xml is kind of obvious, right? Usually it's pretty well reviewed. It gets changed. So I was like, that's kind of a noisy channel. And I was having trouble. I was like, how can we get something to run on the build server from a normal Java developer's perspective? And then I thought, Jesus, the test case. Test case is code that runs, and when you run the build server, you run all the test cases. So there's some report that says 3 tests failed, and that goes out to all the developers, and somebody gets yelled at, says, hey, you broke the build. Well, those test cases are code. They run on the server, and they're running on the build server, and they're running outside any sandbox, so they could do whatever they want. So here's an example of a little test case. And so in Java, all you have to do is define this extends test case here, maybe put a little annotation here. There's a couple different ways to do it. But in this case, we've got a method that calls test Trojan Java, and all it does is just Trojan, and it passes in the root directory. So we call Trojan. This little code it recursively walks all the files on the build server, and if it finds a class file, it Trojans it. It replaces it with a version that now has our toString backdoor in it. You could be a little more selective than this, but no one is going to review this. Nobody looks at test cases during a code review. So this could be a potentially pretty serious attack. If this worked, you would Trojan all these class files, and then they'd get zipped up, jarred up into a jar file and deployed to production. This could be pretty devastating. And I wanted to talk about how these continuous integration servers work. There's another aspect of them that I think is kind of dangerous, and it's this dependency resolution capability. So in the old days, when you built a Java file, you'd have to go download all the jar files that you need, that you're using, and you'd build them in, you'd have a lib directory, and you'd list them all out in there. Well, those days are leaving. I mean, they're not all the way gone, but they're on the way out. Now, if you're using Maven, Maven will automatically resolve the dependencies that your application has. So in your application, you define, you might say, I need a certain number of libraries. You might say, I need log4j, I need anti-SAMI, you might say, I need Disapi. It's different libraries for Java. Those libraries in turn may depend on other things. So instead of having them all stored locally, you want the latest versions. So now you go out to this dependency management system and you fetch all the latest versions of all those jar files. And you bring them down and you build them into your application. Well, needless to say that it's quite complicated. This is just a tiny, tiny piece of the dependencies in one part of the main Maven repository. If you can find a nice dependency that a lot of other projects are depending on, you can get your code included in a whole bunch of different projects. So now the exercise is not going after log4j directly. Now you go after one of the dependencies, like whatever the weakest one is that's attached to a lot of programs. And then your code will get sucked in and included in a lot of different applications. So the solution is really to maintain your own repository where, if you're using open source stuff, you want to bring it down and build it from source and then put it in your own repository. Maybe you even sign it yourself and use a trusted repository rather than just downloading code from all the heck over the place. So let's talk about a few things you can do to keep malicious Java code out of your enterprise. It's not an easy problem, but I found an article by Bruce Schneier from a few years back where he talks about the problem of insiders. And in general, he talks about, what can we do to minimize the to minimize the risk we're taking with insiders. And he's right up front about it. He says, look, we have to trust insiders. They have all the they have all the keys. He points out 5 different techniques, and I've sort of interpreted those a bit and exploded them, the middle one there, into 3 sub practices. But I think there's some research that we need to do here on how we minimize the risk that we're taking when we use insiders to build code. So the first thing is limit the number of developers, and this is kind of obvious. But when you look at some of these open source projects that have hundreds or thousands of potential developers on them, I think we have to be a little bit circumspect about using that code in our enterprise. I don't know if it's reasonable to trust our enterprise to all that code, which is essentially what we're doing. It might be worth writing that functionality ourselves, with our own people that we know and trust. You have to find trustworthy developers, and currently most organizations, maybe they do some kind of background check, but more likely, they're outsourcing software development to people that they don't really know, they don't have a good reason to trust. And I worry that the solution that people will look for is to just do more rigorous background checks. We need, a full polygraph test and all sorts of things. I don't think that's the right route. I think the right route is to build trust with developers over time by not pissing them off. Don't treat them like crap. Don't give them a reason to attack you. Trust is something that builds up between 2 parties over time. And frankly, there's developers out there that aren't treated really very well. And it wouldn't surprise me if some of them are malicious. I think probably the safer course of action is to try to minimize the risk that way. Now, under limiting trust, there's a few, I sort of broke it down by phases, right? I want to limit the trust that we're giving developers during coding. So when developers are writing code, they've got quite a lot of trust. They can invoke, virtually any API. They can do, access lots of different business functions. We can limit that trust a bit. I like what Google did with their App Engine, which is their part of their cloud platform, right? Instead of publishing the whole Java API, which is enormous and incredibly powerful, they published a subset of it. Just the stuff that most people use, but it restricts you from doing certain things. And actually, it's a lot of the things that the sandbox would have prevented you from doing in the first place. So that's something that enterprises could learn from, right? You could, in your enterprise, not publish, not let developers have the whole JDK. You could make a restricted rt.jar that only has classes that developers actually really need. So you could strip out the B cell, for instance, and a lot of other stuff that's in there that you don't really want developers accessing directly. You can also limit trust during the build process. And so I had some ideas here. We've got some customers who are wrestling with this right now, right? They want these new tools, these new fancy build tools that'll give them all these dashboards and reports. But they're struggling with how to deal with the risk. And so I thought about it a little bit, and I was like, what if you had a separate process for doing a build with all the bells and whistles, and then a separate process, once it's past all that, a separate process that you run on a trusted machine that basically just runs Java, C, and jar tools to build your software. It would require a little extra effort, but then you could build more trusted executables in the build process. And if the fancy schmancy build tools want to Trojan stuff, they can. Great, it's not going to affect the final code that you're running in production. I skipped one thing in finding trustworthy developers. I do think that accountability is really important. So I was talking about you've got to trust your developers and you want them to trust you. Well, that's great, but having accountability is not a bad thing, right? So we want to make sure that every piece of code, every line of code is traceable back to who's responsible for creating that. I think that creates a massive disincentive to attackers for putting malicious code in an application. All right, so jumping forward now to 5, what can you do to limit trust in the operations when you're actually running these applications? Well, the first thing that I'd recommend is using the sandbox. The sandbox stops a number of these attacks. All the techniques that I mentioned for turning data into code, the sandbox stops those. Even if you're running a really crappy sandbox without a very narrowly configured policy, you can restrict a lot of these attacks from running. So you don't have to get super granular about it because, frankly, writing a Java policy that's very, very tight is difficult. I mean, it's a real pain in the ass. But you could write a pretty loose one that says, hey, these jar files can't use the class loader, and these jar files can't call the Java compiler. Things like that you can define pretty well without a huge amount of trouble. Bruce mentioned this idea of creating overlapping trust. And the idea is that, so he gives a movie theater example. He says, why do you have to buy a ticket from somebody and then 10 feet away have someone else collect the ticket and rip it in half? Well, the reason is entirely procedural, right? They want you to have 2 steps so that no one person can, sneak people into the theater. Well, we can sort of adapt that principle to our code development, right? We can say, hey, we want a couple people involved with every line of code. So pair programming is one thing where we make people aware of some of these, these malicious attacks and some of the things that you need to look for. We can do other things when we're programming, like having mandatory peer reviews, so pair programming and peer reviews. Some of the practices we can use to create overlapping trust associated with our code. I think that creates some real disincentives to trying to do some of this tricky stuff. And then the last thing is we need to have processes for detecting malicious code. We have to do this for regular vulnerabilities anyway, right? We need to find instances of SQL injection and cross-site scripting and command injection and so on. That process is where we should also be looking for malicious code. And we need to start somewhere. I think this is fairly early on in the research. I think we'll get more efficient at this. But we need to start configuring the tools to look for this stuff. So I've talked to some of the static analysis vendors, and they have thought about this problem. They may not deliver the rule pack with their standard stuff, but you can ask them for it, and maybe they'll help you. But we can configure those tools to look for some of this shady kind of programming, and if we're aware in our validation process, we can find these problems and eliminate them from our apps. So, after all this, I look back on my week of experimentation here, and I think, if I was really doing this, I think probably what I would do is I would, instead of using these complicated techniques to introduce malicious code, I think what I would really do is introduce a flaw that looked like I just made a mistake. Like I say, oops, I forgot to check this, validate this parameter, or I didn't catch the exception right, so this authentication method fails open. Like some of the stuff that we've got in the OS top 10, I think I would just put one of those flaws in, and then if anybody found me, I'd have a nice plausible deniability capability. I could just say, hey, I made a mistake. I didn't know about that. But nevertheless, I do think that these kinds of attacks are easy and likely and pretty serious. So just in case anybody's tempted to try any of this stuff, I will warn you that if you're caught, it's almost certainly a crime. Martha here is the poster child for the insider attack. So keep in mind she ended up in jail. So I'll be happy to take some questions. That's it. And please don't forget, if you would join us down in at the OWASP thing, in the general room. It starts in sort of 15 minutes after this presentation. Questions? In the back? Yeah. Yeah. He wanted to see the URL where you can download the paper and the code. So it's all here, and the presentation is up here as well. Sorry. There you go. If you can't read that, it says aspectsecurity.com/documents/enterprise-java-rootkits.zip. It's all in there. Any other questions? Yeah. So if you're using open source code, you're taking some risk. I mean, if you treat it like your own code that's untrusted, you want to put it through the same kind of verification that you would put on your own code at a minimum, right? So check it. Do code reviews on it. Look for vulnerabilities and malicious code. You may want to compile it yourself and build a trusted jar file. That way, if someone's Trojan the class files, you can protect yourself against those kinds of attacks. And you should sign and seal your jar files. There are two different capabilities built into Java that help protect people from injecting malicious code into an app. Dennis?
Do you think we need more research on how to exploit this to reservoirs or how to protect it?
Well, they go hand. So the question is, do we need more research in how to exploit this or how to defend against this? And I think they go hand in hand. So I've spent my career being on the sort of the builder side of the builder breaker thing. So this talk for me is a little bit of a stretch, but I think in order to really understand something, we've got to break it and figure out how to build protections against it. And I really think we've got to do both. So if there's interest, I want to start an OWASP project to start cataloging different techniques here. Let's figure out, what are the different categories of techniques for doing malicious code, and what techniques can we use to address those kinds of risks for enterprises. Yeah.
Versus the open source question, what can we do to defend ourselves from same sort of issues with closed source stuff, where we can't even look at the source code when we're running?
Yeah, that's a good question. I mean, if you're using, the question is, what can we do to protect ourselves against closed source? Like if you buy a library from a commercial company, how can you protect yourself to make sure that there's no commercial code in there, no malicious code in there? One of the things that you can do is, in your contract for that code, you can put terms in there that create liability for people that, if malicious code is found, then you've got some recourse against the company. And so that will help force those companies producing those libraries to prevent malicious code in their own apps. But another thing you can do is just ask, what stuff are you doing to make sure that your library is coming out secure? Are they training their developers? Are they doing good security testing? Do they have an application security program in place? Get some details about that, and then use that as one of your buying decisions. Like, I wouldn't buy software from a company that doesn't at least train their developers in secure programming. But you got to ask if you want to know. But pretty much we're screwed. I mean, that's a little hand waving, but pretty much we're a long ways from where we can really rely on code that other people wrote, which was essentially the prediction that Ken Thompson made, right? He said, unless you wrote it, you can't trust it. Yeah. Question? Yeah, sorry. Yep.
How prevalent have you found issues like this? Not asking for divulging confidential information, but is it widespread, very limited, somewhere in between?
So the question is, how often do we really find this in applications? And the first thing to understand is that unless you're specifically looking for malicious code, you're probably not going to find it. And so when we scope reviews, we have to make priorities. Many of our customers are not willing to pay for a malicious code level review because it's harder. That said, we have found it on occasion in the past. We found instances, more instances of Easter egg kinds of things than things that we could specifically say is, no, that's a backdoor that would be designed for malicious purposes. But think about that. If we find but we find vulnerabilities in every application that we look at, right? And so only a crappy attacker would put in a backdoor that when we found it, we would know for sure that it was backdoor. Like they never say backdoor here. They always are like, a very subtle programming flaw that a developer could easily say, well, I just made a mistake, right? We find those simple mistakes all the time. So were any of them put there maliciously? I don't know. And I don't think anybody's ever going to know. But that's, I think, a significant reason why we don't find it more often. Yeah. So I didn't get quite all of that, but I think it was about, shouldn't we build more knowledge about this into the tools and into the process? Well, like I said when I started, doing source code analysis it's both humans and tools combined. You have to have both. And both sides are going to have to improve if we want to be able to find these kinds of problems in our source code. There are some things that, no problem is ever going to be absolutely detectable with automated tools. So you're never going to run a tool and it's going to say, here's the problems. And frankly, no human reviewer is ever going to be able to do a perfect job on a source code analysis because these apps are just too big. I mean, we're looking at apps that are, 1, 3, 5 million lines of code, and we've got, a month, 4 weeks. So it depends, 8 weeks. It's not enough time, right? So we both have to get better. All right, I think that's it. Thank you all very much. Appreciate it.